Section 15.5 talks about triple intervals in rectangular coordinates, and identical to what we just did in area. Now, if I look at a rectangular box, I will break this. And the list goes on. And the list goes on. So I'm looking at those cubicles, and if I take one of them, if I take one of those cubes inside, supposedly one of those, because I'm going to break this sideways as well. So I'm running a laser beam. I'm going to take this and look at that. That's going to look like one of these rectangular boxes, in which this is delta y, this is delta x, and this is delta z. And as you can guess, volume is delta x, delta y, delta z, and this is sub I, j, k, and I could do the same for those. And the volume turns out to be I'm cutting the derivation down. Normally I derive this fully. It's a lot of fun to do, if you know what I mean. And hopefully by now we know it well. If you want it to be volume, shrink this a bit. If you want to find the volume, you just make sure that you put a 1 there, and region B would be this entire region. So, deriving this is really good. It says derived in the book. You could glance at it if you wish. It takes a bit more time than we have. So, now when I look at this, there are a lot of different ways I could find volume, and let me elaborate. So if I'm glancing at this, and I'm going to copy that, normally I like to come up with my own, but under the circumstances, we're going to really cut down on some of the theory. For now, just in the beginning, oh boy, this is glacier. Why is that? Okay, there we go. That's better. If I want to find the volume, I would say this is the triple interval. Now, if I run a laser beam from negative to positive, do you see where it pierces? It pierces from f1 of xy, which means the innermost is dz. It's gonna run all through, and it's gonna exit out of z equal f2 of xy. Once you do, dz, forgive me. Once I do that, then I am left over region R dA, region R being right there. Now when I take this, I have two options. When I take this and I really put it on rectangular coordinates, it's gonna look, it's gonna look like this. Based on what we have over there. it's going to look like A to B, and it's really something like this. Now, can't I run this from A to B? So I could say this is fixed by me saying I'm running this from the Z direction. That means I'm looking top to bottom. I'm looking at this from the top and I'm trying to figure out what I see. This is all I see. I only see this region, whatever that region is. So this is R. Now, can't I say this is dx, and x runs from A to B, and in that sense, y would run from y equal h1 of x, and it's going to exit out of or to h2 of x. Or somebody might look at this and say, wait, time out. We just did area, and this area right here I could do in terms of x or y, since you already have the z. I keep on writing dy, you guys forgive me, it's really dz. Since you have dz fixed from f1 of xy to f2 of xy, now I really don't want to look at it this way. I really want to look at dy being the outsidemost function. That's from C to D. And wouldn't you say then x is going to run from and in this case x runs from some g1 of y, and it's going to terminate at g2 of y. If this is confusing you, basically this part and this part is the homework that we just finished. That's the double integrals we just finished. This is looking at this from the top down. So we're going to practice that on the next few problems. And that's going to be the lecture for today. And then we're going to come back, finish the section up the next time, and talk about looking at it from the x direction or the y direction. I should copy that one. That looks nice. Dang it, I didn't pay attention to that. That's okay. So if I look at problem number 4. Okay, I'm going to make that a bit bigger. Page 929. So what does this say? It says, write 6 different iterated triple integrals for the volume of the region in the first octant enclosed by x squared plus z squared equal 4 and the plane y equals 3. Evaluate those. Let me check really quick something really fast. Okay, I'll tell you what we're going to do. We're going to do number 6, and we're going to hold on number 4 for the next set of... I'm going to restart this. It's taking forever for me to do this. So let's do number 6. Number 4 we will do in the second half of this lecture. Not for today, for next time. This says, volume inside paraboloid beneath a plane. Inside paraboloid beneath a plane. Okay, so plane is above. Let D be the region bounded by Z equal. Now, the graph is not a must, but you must be able to visualize it at least. Z equal x squared plus y squared. And Z equal 2y along the y-axis, 1, 1, 2. And this is a plane cutting. It's going to trace along the x-axis. So you have a paraboloid coming out. You have something coming out. And the line is cutting at it like that. Right? So when I look at this from 3D, I'm looking from the top down. I'm trying to figure out what that looks like. Now, if you're having a hard time visualize this, I already did this in, there it is, the paraboloid and x equal to, so from the top, that's what it looks like. That's what you're going to see along the xy plane. We'll get to that in a minute, but if you look at it, it looks like this. So, the most important aspect of this is you being able to visualize it, nothing more. And if you can't, then that's really what you're going to be working on until you start being able to visualize this. There's no way around it. Visualizing the problem is half of it. Oh, come on. My time's almost up. I haven't even done a problem. Strange. Alright. So, the way they want us to do this, they want us to do this with respect to Z, which is really what I want to focus on today. And they say, let D be the paraboloid, and write a triple integral, the order of this that finds the volume. So, okay. If I look at dz, meaning I'm looking in the z direction from negative to positive, do you see where it hits? This graph begins from x squared plus y squared, and where does it exit out of? It exits out of the plane, and the plane is z equal to y. And once I do that, now it's a matter of me figuring out what the two dimensions look like and writing this twice. So that is the triple integral x squared plus y squared 2y dz. Well, obviously, one time I'm going to do a dx dy, and the other time I'm going to do a dy dx, because that's what they want. Well, let's see how this works. If I take z equal x squared plus y squared and z equal 2y, that means 2y equal x squared plus y squared. This is the intersection. 0 equal x squared plus y squared minus 2y. So if I add a number to both sides of the equation, this will be x plus y minus 1 squared equaling 1. I know that's a circle centered at 0, 1 with a radius of 1. So the circle looks like this. And we saw that already when we looked at the 3 dimensions. We saw that right there. That you must get. And now it's a matter of thinking, alright, if I'm going to do a dx, x is going to run from negative 1 to positive 1. And that means y is going to run from what to what? Y minus 1 squared is going to equal 1 minus x squared. So y is going to equal plus or minus the square root of 1 minus x squared plus 1. So that's going to go from 1 minus the square root of 1 minus x squared to 1 plus the square root of 1 plus x squared. And if I run sideways, this is going to run from y equals 0 to y equals 2. And x is going to run from, what would x equal? X would equal, moving this to the right, plus or minus the square root of 1 minus y minus 1 squared, from negative the square root of 1 minus y minus 1 squared, to positive the square root of 1 minus y minus